Hello guys, welcome back to my channel, and today we are going to talk about a new paper called Towards Versatile Graph Learning Approach from the Perspective of Large Language Models. So let's get right into it. So as a lot of you guys know already, right? So graph data is typically used like in everywhere, including things like social network, modeling chemical molecules, and traffic modeling, and so on. So, right. Being able to make predictions based on graph data is extremely important, right? And 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 there's a new study that show that large language models can offer potential solution um, to give human-like uh, intuition, right, for understanding these graph data structure. So this paper proposes a new concept for designing graph learning methods with LLMs, right? And they're stated right here that it's with a particular focus on the where and how perspectives. Okay, so there's two parts here. So the where, the summers four key learning procedures, including task definition, graph data feature engineering, model selection, optimization, deployment, and serving. All right, and then the described. Okay, they explore the application scenarios of LLMs in these procedures. And now time for the how perspective. So they align the capabilities of LLMs with the requirements of each procedure. And then finally, they point out the promising directions that could better use LLMs towards graph learning methods. And the code is available on GitHub. So do make sure to check it out if you are interested. But right now, let us go straight to the conclusion and let's see what they have to say. Exploring the feasibility of employing LLMs in graph learning problems is a promising direction. In this paper, they propose a new prototype for graph learning approach, and they provide a comprehensive overview of existing methods joined with LLMs following the graph learning procedures and the different ability requirements for LLMs. There's explore the feasibility of using LLMs in graph learning pipeline, test definition, graph feature learning, and so on. Right. Okay. In each procedure, they categorize the methods following the involvements of LLMs and provide detailed discussions about these approaches. And they also suggest a few future directions for LLM-based graph learning procedures. So, okay, right. So all of these are just basically repeating what the abstract says. So, okay. How about if we go into the future directions now? Okay, the developments of LLMs and the potential applications are fast growing in recent years. Beyond existing methods, there are several promising directions, okay, that could be explored on graph data. Number one, the ability quantification of LLMs in understanding graph structured data. Okay, and now they're stating here, which I think is important. Let me get the correct color here. All right, red should be enough. Okay, there is an absence of systematic evaluations regarding the ability of LLMs to comprehend graph structured data. That's exactly right. To be specific, LLMs are trained with natural language where while the graph structure, the key in graph learning are represented as adjacency matrix in general and are new modality for LLMs. So there's a couple of existing approaches, namely GPT for graph and TLG. attempt to describe graph structures with natural language. Okay, so these um, references are quite important for me. So there are some existing works that describe graph structures using natural language. Okay, and then evaluate the effectiveness of the graph structure reasoning tasks. On graph structure reasoning tasks, for example, node degree prediction, graph diameter, and clustering coefficient. But they argue that these measures are not enough to capture the capacity of LLMs to understand graph structures. Okay, and they're saying that firstly, the descriptions can greatly impact performance, obviously, which can result in inefficient robustness and reliability. Moreover, this lemon test, which is crucial in assessing the comprehension of graph structures, should be considered to theoretically validate the effectiveness. Okay, so what they're saying is that maybe perhaps instead of doing like node degree, graph diameter, and so on, how about if we use this approach right here called the lemon test, right? So from what I remember, the lemon test is like something like yeah. So it's a graph isomorphism test. So basically, what you're proposing is that okay, how about if we like test the LLM, right, by basically giving it like two graphs, which are basically the same graphs, but but um yeah, but it kind of looks different, right? Right. Right. So we want the neural network to be able to distinguish different graphs, and that in a way should help us to know whether the LLM actually understands about the graphs topology in general, right? So that's what they propose, which is interesting. And now let's go to the next one. Okay, large graph foundation models. Accepted for employing LLMs in solving graph learning tasks, designing graph foundation models, and scaling up model parameters is a promising direction. Okay, so to be specific, existing methods have explored GNNs and graph transformers on single tasks, comparing foundation models in natural language. Challenges in large language models are the lack of pre-trained data and the large-scale backbone architecture. And now, not to mention that if you try to scale a graph neural network, right, it usually doesn't work due to oversmoothing, where as each layer has been passed, all the node representation converge to the same thing, to the same values, right? Which isn't good at all. And we don't see that happening in large language models. So that's that, right? Okay, next. Universal graph learning agents. Okay, and now they're talking about agents here. Okay, anything with agents, I guess. Okay, LLM agents are a prominent research topic in both academia and industry due to its potential emulating human-like decision-making processes. Okay, in graph learning, LLMs can be like a research assistant when facing different learning problems. For example, decomposing graph learning tasks, writing and executing graph learning procedures, or arranging graph learning tools when facing the task. I don't know about you, but this isn't really like I wouldn't say this is um, Yeah, I have some doubts about this. I mean, by that point, if you're able to create such agent, you would have, you might as well just focus on making a AGI at that point. Yeah, so I think that's a way out of scope anyway. All right, moving on. Okay, so how should we cover this paper? I guess we should quickly skim through the introduction. All right, graph structured data are commonly used, blah blah blah. Okay, so they talk a lot of things, blah blah blah. Okay, all these aspects lead to the challenge for human experts in handling graph learning that's suited for different tasks, graphs in diverse domains, and can efficiently conduct the pipeline as few as possible assistance from humans. All right, so there's a lot of things here. Yeah, and I mentioned about AGI, which of course, why not, right? So, yeah, the numerous advantages of LLMs, right, is that, for instance, to harnessing the preserved knowledge, different graph learning tasks across various domains can be unified into text descriptions, which subsequently employ LLMs to acquire predictions. So basically, they're saying that the LLMs are essentially like a unification, right, of all different graph um, graph learning, right? Graph learning tasks, right? Because it does kind of know how to perform these operations, but not necessarily like 100% accurate, but it is able to do that, right? So yeah, especially with like a textual, yeah, there's a spelling error here that's supposed to be textual, right? Textual attribute graphs tags. Okay, so right. Okay, development. Okay, blah 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 blah. Okay, all right. So it's just some questions, and it talk about basically the same thing from the abstract. All right, let's take a look at figure one here. So figure one is okay. The prototype of versatile graph methods joined with LMs. LMs can be used in sequential graph learning procedures in these columns with the increased requirements for LMs in different rows for each procedure. The rows can be further developed with exploration of different abilities of LMs. Okay, so so right here, what they basically have, okay, so we start off with like 0 LLM, right? So right here, it's only human experts, and yeah. So for example, task definition with human experts. So the human has to create the task manually, right? Trying to define the task to the machine learning model by themselves, right? Which is a typical approach that's used until now. And for feature engineering, yeah, humans got to do it as well manually. It's like, okay, right? If you want to describe the data, then you need to extract some kind of a fingerprint, right? Um, the, or something that's like special um, about the data such that it is useful for any kind of prediction, right? And next, model selection and optimization. So obviously, we humans have to like, okay, we have to train each models and then make the comparison by our, ourselves. And that's also the same for deployment and servicing as well, where the humans have to deploy the model again by ourselves, right? And then we have to manually make sure that the model actually works. Okay, and now here is, I would say this is where we are right now. So here, okay, sorry about that. Just a minor hiccup there. Okay, task definition with experts. Okay, right. So humans can use LLMs, kind of similar to how we use ChatGPT to help us out, and and textual feature construction and encoding. So basically, there's a lot of these features, right? From the raw data, we can use ChatGPT to extract the features from the graph using text, right? And what do we have? Prediction generation with LLMs and graph learning algorithms. Okay, so as you can see right here, okay, so the predictor approach basically just using the LLMs to make a prediction directly, right? Whereas for co-operator, you use both LLMs and graph neural networks to make to, to cooperate to make a single prediction. Whereas with the advisor model, it's basically just like using, I think it's either using the LLMs to before feeding the LLM output into the GNN, right? Or it could be the other way around as well. So okay, right. And responses you generated using LLMs, kind of like ChatGPT. And now the last part right here, right? Which is basically another step of fully automating everything using LLMs, is that the LLMs can like plan and decompose different tasks such that it can follow through its own plan and then executing each step as, as it goes on, right? and a graph node extraction and connection with LLMs, and then obviously model and hyperparameter selection using LLMs again. And we actually seen, and I actually make a paper, right, about this approach. I think it's called AI is making AI. Yeah, that's the video that I make specifically about this approach. Yeah, if you're interested, make sure to check that out. But anyway, okay, and then we have model deployment with LLMs. That all makes sense. Okay, so right here, let me see what they got actually. Okay, so they got some things right here. Mm-hmm. Right. Just give me a second. I'll, I'll be right back. Okay, sorry about that. All right. You know what? Let's get right into it. Okay. Let's get right into it quickly. Okay. So this is the preliminary machine learning on graphs. Okay. So the graph data can be represented as a collection of nodes and edges. All right. So what they're trying to solve, okay, task definition, experts formulate problems P into specific graph learning tasks T. Example, predictions on nodes, edges, subgraphs, or the entire graphs. Okay, so they're formally defining every single problem. Interesting. Okay, so feature engineering. Experts select and combine or transform features to get better accuracy. So, for example, different frequency bands are designed to eliminate certain graph Fourier modes. Besides, it can be automatically achieved with auto LLM, which involves selecting appropriate feature sets and combining them in a data-driven manner. Okay. Model selection and optimization, excerpt select and train architectures AW. Right, okay. So obviously we humans do that, where A represents the selected architecture with the trainable parameter W star. In addition to designing and tuning architectures with human experts, right, they can use something like neural architecture research, NAS, and hyperparameter tuning approaches, obviously. And then they talk about deployment and serving, right? So experts deploy models and generate results R to serve users in graph learning problem. All right, so those are the three main problems that they're trying to tackle. And now, conceptual prototype. We propose a prototype such as, okay, so they focus on where it can be used. I assume where LLMs can be used. And then they must be talking about, okay, right. So it's essentially talking about figure 1 and how to use. Okay, yeah, so essentially we already covered that. It's in figure 1, but in general, right? Okay, and they say it is necessary to note that the potential of the abilities of are still being explored. So basically what they're saying is that this figure doesn't tell you everything about what you can do with LLMs, obviously, right? So yeah, so it can be further expanded as time progresses, right? All right, so and it talked about how their paper is a better survey paper than the other survey papers. Whatever. Okay. So, oh yeah, actually, think about it, right? This is kind of like a survey paper, essentially. They don't really propose anything new, right? Another survey paper. Okay. Let's just call it that, right? But it does have like a few nuance to it, which I kind of like. All right, let's carry on. Task definition. Task definition transforms the learning problems in real world into solvable tasks with current machine learning techniques. Okay, so I'm just looking through to find if there's like anything interesting about this because it's pretty self-explanatory at this point. However, graph structured data, which stems from different domains, unlike textual data, presents a unique challenge. The learning tasks related to graph data necessitate diverse configurations for individual tasks. Okay, so from the literature, right, a lot of these different approaches, evaluated LLMs in understanding and formulating graph reasoning tasks over different graph datasets. Structure theory GL proposed a LLM-based planning agent and map uses structures. Okay, we're back. Okay, and then map the user's data into different graph learning tasks. Given the experiments over different tasks, the feasibility of LLMs in planning and understanding graph learning. So yeah, so it's basically something like graph of thoughts, some kind. Yeah. So yeah, okay. So that's that. And then feature engineering. So feature engineering is all about, okay, another spelling mistake here is about combining and transforming features to become effective features, which then you can use to make better model to predict the graph data, right? So LLMs, obviously, they can generate textual descriptions of the graphs, and then you can encode them into this vector space, yeah, which then you can do a lot of things on it, obviously. So, and it talk about how one can construct the text data from it. But essentially, it is to take a graph, okay, and you define a graph, a text graph as a word sequence, right, that is used to describe the nodes and edges of the graph. And then you also have to define a structured textual graph, and then say it is a combination of the structured graph and the text description of the nodes. Basically, it's a text attributed graph, TAG, right? So this type, okay. So to say, firstly, for this TAG graph, right? The textual descriptions and explanations of the components of the graph can be generated by LLMs and used to improve its accuracy. To be more specific, right? The text for the nodes, right? And then also they can describe the entire structure using natural language. So yeah, so basically the LLMs can generate text features that describe the data, right? Which is something that the graph neural network cannot do right now. Okay. Okay. Right here. Okay, and there's this approach of like sampling k-hop ego subgraphs, and then describe the labels and features of the nodes in each hop. And then this TLG provided 11 types of text description functions, right? LLM for molecule describe molecules with smiles and explanation of functional groups, chemical properties, potential pharmaceutical application generated by ChatGPT, right? But to be honest though, if you just need the smiles, you probably don't need ChatGPT. But okay. So, and that's that. Right. And if you want to get the embeddings right, there's a lot of different approaches, such as a sentence word, right, Roberta or Palm, but I typically use sentence word because it's available on Hugging Face and you can use it easily. So okay, and that's the summary and the discussion right there. Not that important. Okay, next, 3.3, model selection and optimization. Right. So let's see. Okay, so the core objective of this is to select and train models that can be used for downstream tasks. So it's basically selecting and optimizing A given data G and task T. Okay, so basically selecting the appropriate architecture for that, right? So, and to say that LLMs can be used to encode, so it can be used to make decisions, right, about selecting which architecture. At least that's what they say right out. So, okay, LLMs as predictor for textual graph GT. Existing methods employ open or closed source LLMs. Okay, so they call LLMs as architecture of LLMs, ALLMs, to generate the prediction results are of graph learning problem P. Graph text, okay, uses ChatGPT to predict node labels. Okay, right. We read that before, right? Yeah, yeah, it's pretty much the same as before. Nothing much new. Um, okay, so let's see if there's anything new here. In conclusion, when dealing with text graph, using we can use LLMs. Yeah, so there's nothing interesting there, unfortunately. Okay, now next, LLMs as co-operator for text attributed graphs. Just give me a second. Let me see if there's anything more. Okay, we're almost there. Good. Okay, ALLMs and AGLAs. Yeah, and as you can remember, Figure 1 already talks about this co-operator framework, right? But they are going to define it a bit more formally, I hope. Okay, so the first approach is to use the LLMs to generate the text and then have a graph neural network to use those texts to generate predictions, just like I say, right? And of course, you need to use something like sentence BERT in order to convert the text into an embedding vector such that you can assign the embedding vector to each node and edges of the graph. So that's a pretty common approach, right? So for example, someone has used DBERT to decode the texture descriptions and explanations, and then use reverse GAT to learn graph attention to learn graph representation. Okay, and the next one is alignment-based methods are co-operated by aligning the textual and structural embedding space. Okay, so basically you have the graph space, graph embedding space, and you have the text embedding space, and how do you unite them, right? So, for example, G2P2 adopted three levels contrastive learning when pre-trained with graph convolutional neural network and transformer. Right. So they use contrastive learning, okay, and they call it three levels contrastive learning. I would assume that it has to be something like, oh yeah, is this generated text in the embedding space? Is the text close? Is the text that's representing this graph closely matching together, or is it closely matching with like a completely different graph structure, right? So the idea is that we want the graph and the text that represent the same thing to be close together in terms of in the embedding space, right? But for something that's completely different, it should be far away. That's the idea behind contrastive learning in this case. So okay, so someone trained GNNs and BERT in a nested manner, okay, right, and grab the structured information from GNNs to enhance the BERT. Okay, so this approach is the other way around, is to let the GNNs make some embeddings which then can be fed into the BERT model such that the BERT model can make a more accurate prediction. Yeah. And finally, LLM-centric methods use graph learning algorithms to extract the graph information and then map it to the text space of LLMs. Okay, so as you can see, these are the different approaches right here. Right, so contrastive learning in the middle, whereas you have like graph neural networks first, then LLMs, or the other way around, right? LLMs first, then the graph neural networks first. Right, and that's that. Pretty cool. All right, but I think this approach is much more interesting, right? But obviously, with like contrastive learning, it does have its own drawbacks, right? For example, it really relies on the batch size that you're using. right? And I've seen some papers where they use like thousands of batch sizes, which is like really difficult to operate unless you have like a huge compute cluster with you. But that's a story for another time. So okay. Blah 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 blah. Okay, right. Um. Okay. Let's see. LM as advisor for graphs. For structured graphs. Let me see. Okay, right. We are almost there. So okay. Based on the structured graphs without textual data. Okay, right. Let's say if you don't have text data, right? LLM as graph learning research assistant in selecting models. Okay, so it's that. Okay, so basically, and like I say, I already covered a paper that does exactly this, right? So basically, you have GPT-4, and then GPT-4 can help to design what kind of like GNN architecture that you want, right? And that paper which I covered before, it is like, okay, do you want a graph convolution operation here, or do you want an attention operation here, or maybe the other way around? And then after it makes, after it constructs, right, a model, it trains it, right, and it gets a set of results based on a set of architectures that it made, and then it can use that as a feedback mechanism, and it goes on and goes on until it gets the right architecture, right? Okay, so it used a fixed search space and let GPT-4 select and revise GNNs from this space to make better architectures. Right, and someone else configured the search space to automate conducting graph learning procedures. Okay, and they're talking about graph foundation models. Right. Graph foundation models, again, motivated by pre-train and prompt. It's a thing. So they're trying to do something here, such as a graph prompt, something similar to what LLMs already have, which is prompting. So they're trying to have something like graph prompt that tries to unify graph learning tasks on node, edge, and graph levels with link prediction tasks, then pre-train the GNNs on different tasks. Okay, right. In the prompt tuning stage, graph prompt learn the prompt vector. Okay, right. So it is essentially trying to mimic um, the what the LLM does, right? So imagine if you have a text, right? And then you can convert it into a text embedding, and then you can use that text embedding and put it inside the GNN and directly train the GNN to know exactly what kind of prompt corresponds to what kind of task that you're interested in. I think that's what it meant, which is kind of similar to NLP in general. Okay, and then now we have summary and discussion right here. Okay, and obviously they're talking about some drawbacks, right? So okay, LMs can play different roles depending on the type of graph that you're giving it to that you're giving it. Okay. Okay, so LMs have difficulties, right? So such deficiencies accumulate over time. Lack of theoretical justification. I mean, to be fair, theoretical justification, it's not really existent in deep learning. But yeah, but I mean, there are some mathematical proofs, but it's usually like two layers or something. abysmal like that. So yeah. Okay, blah 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 blah. Yeah. So I think that's about it. So I hope you and I learned something new today. So yeah, so overall, this is a survey paper, and I think it's quite useful if you are just getting started in this field. I personally have gone through a ton of these graph neural network plus LM papers, and I think there's a lot of work that needs to be done in order to integrate both of them in a much better and beautiful way. So yeah, so if you like this video, make sure to like, comment, and subscribe, and I will catch you all in the next one. Bye bye.